So last couple classes I've been reviewing how you numerically solve a single nonlinear equation. So the point equation f of x equals 0, where x is a scalar and f is a scalar value function. So now we're going to using fixed point iteration or Newton's method, or secant method. So now we're going to generalize this, solve a system of nonlinear equations. So I'm still solving f of x equals 0, but now x is n vector and f is a vector value function, and variables in and variables out. So here's the notation. So my function, big F of x, has n component functions, each one of a function of n variables. So each one of these components, like little fi, or f1, f2, etc., takes n variables in and puts only a number out, but then we gather all those together to a vector. So these are the component functions of capital F. Keep in mind my convention that I tend to format vectors or vector value functions in bold. Okay. So how do we generalize the method that we've seen for a single nonlinear equation in the general case? So I'm going to start with fixed point iteration. So f of x is 0 equals 0 is once again rearranged as x equals g of x. So fixed point iteration has the same form as before. So new x is equal to g of previous x. It's just now everything involved is a vector. Now, before I would write, one way to write g of x, define g of x is equal to x minus, I previously had a non-zero scalar lambda times f. Here we're going to generalize that notion. Instead of having a non-zero scalar times f, I'll have a matrix A, so it's a constant matrix independent of x. But this time A is invertible, also known as non-singular. So that way, by making sure that A is invertible, as before, x is equal to g of x, if and only if f of x is equal to 0. So the two equations are equivalent if A is an invertible matrix. Okay, so that's how the most straightforward way of defining G is generalized to the case of a system. Now, the invertible part is important because if A was singular, then you could have a situation where f of x is non-zero, but A times that non-zero vector equals 0 and x equals g of x. So that would be a situation where x equals g of x, but f of x is non-zero. We don't want that. So A being invertible makes sure that this is satisfied, again, if and only if this is satisfied. So when does an iteration like this converge? So I'm going to show you the convergence conditions for single equation and system side by side. You can see how similar they are to one. So for a single equation, the condition was that if g is differentiable, if the absolute value of g prime is less or equal to some constant L, a Lipschitz constant, and the L is less than 1. And if that's true on some interval AB, and G maps the interval AB into itself, then we have existence of a fixed point, we have uniqueness of a fixed point, and fixed point iteration convergence for any initial guess in that interval AB. So what is the corresponding condition when we have a system? So if we define the Jacobian matrix of G be a matrix consisting of all the partial derivatives of the component functions with respect to all the variables. Notice how the matrix is set up. Each row corresponds to one component function. So first row is all about G1, second row is all about G2, and so forth. Each column we're taking partial derivatives with respect to one of your x's. First column, all partial derivatives with respect to x1. Second column, all partial derivatives with respect to x2, and so on. So here we have all the partial derivatives of all the component functions with respect to all the x's. So this is how the ordinary derivative in this single variable case generalizes to multivariable case, all possible partial derivatives. So, and because the derivative is now a matrix valued quantity, we're looking at a norm. So if the norm of your Jacobian matrix, it could be like a 1 norm or a 2 norm or infinity norm, is less or equal to some constant rho that's less than 1 on some domain D in Rn. And we still have the condition that G maps that domain into itself, just like single variable G maps the interval into itself. So if that's the case, then we have existence of a fixed point, we have uniqueness, we have convergence of fixed point iteration. So the single variable convergence condition generalizes in a natural way to the case of a system. Now, this condition I've given, that the norm is bounded away from 1, that is sufficient for convergence. And this can be shown using, it would be a multivariable Taylor expansion that I won't get into here. But it's sufficient for convergence, but it's not necessary. And I'm going to draw a parallel with something I showed you earlier, back in chapter 5. I know some of you are doing that homework now. For iterative methods for solving a system of linear equations, so AX equals B. So this is our general form for a stationary iterative method for AX equals B. Then the Jacobi, Gauss-Seidel, SOR come from this. So this could be followed as a fixed point iteration where your g of x is defined this way. Just taking this equation and multiplying both sides by m inverse on the left. So this is your g. Now, back when we were dealing with this kind of iteration, what I told you back then was so the Jacobian matrix of this function, which is a linear function of x, is m inverse n. And what I told you back then was the norm of m inverse n being less than 1 is sufficient for convergence. And then the spectral radius of m inverse n being less than 1, I need to fill that in, less than 1, is necessary and sufficient for convergence. But the norm being less than 1, that's easier to check, like if you're dealing with like a 1 norm or infinity norm. Okay, so questions so far about when fixed point iteration for a system convergence? Yeah.
I have a few questions.
Okay.
So there, that Jacobian, well, with a subscript G,
yeah.
But we used to refer to that m, well, inverse of m times n as an iteration matrix.
Yes.
Right. Now, okay. So there you have this, okay, that p or is it rho?
Well, it's a Greek letter rho.
Okay, so is it spectral?
Spectral radius, yes.
Okay, so that condition holds for any norm.
Yes, yeah. Just because the spectral radius is always less than or equal to any natural matrix norm. So do you have a few questions?
Oh, and another question.
Yeah.
Can you scroll up a little? So there we define that g of x, well, yeah, there's a there. Why a has to be invertible?
Oh, okay. Yes, I went into this earlier. Suppose A was singular.
Okay.
A is singular, then there exists a non-zero vector, we'll call it y, such that ay is equal to 0. So let's suppose that, so we could have a situation where f of x is non-zero, but it happens to be a non-zero vector such that when you multiply it by a, you get 0. So then, in that case, g of x will equal x, but f of x will be non-zero. We want this equation and this equation to be equivalent. So that's why we need a to be invertible to guarantee that the only way this term can be 0 is if f of x is 0. Okay. Questions from anybody else? Okay, here's an example of fixed point iteration for a system. We just have two equations. So we want both these equations to be satisfied for some x1, x2. Now, this first equation, x2 is equal to x1 squared, would define a curve in the x1, x2 plane. If you think of x1 as being x and x2 as being y, what kind of curve would this equation define? Just the first equation.
Parabola.
Yeah, so you have y equals x squared. And what about the other equation?
Circle.
Yeah, unit circle. So basically, we're looking at a parabola, y equals x squared, intersecting with unit circle. So what I can do here is, all right. Now, if I choose a positive square root, I can rewrite the system equations this way. So x1 is this from taking a unit circle equation, and then we have the second equation here is the same as the first equation above. So now I have this system in form. The vector x is equal to some function g of x, which comes from the right-hand side. So here's my g of x1, x2 is defined this way from the right-hand sides of these equations. So, so if I consider the domain x1 and x2, both between 0 and 1. So if I plug in x1 and x2 between 0 and 1 into these formulas right here, I'm going to get something between 0 and 1. So, in other words, this g maps the domain D into itself. So that this square for x1, x2 between 0 and 1 is mapped by g into itself. So there's existence of a fixed point. But what I'm going to do is I'm going to define this g in MATLAB. Okay. I put a fixed point for a system. So I define g as a function handle. And I'm going to assume that x is a vector with two components. And the result of g will be a vector with also two components. So I take square root of 1 minus the second component squared. And then I take the square of the first component. So this g is defined based on this g right here. So I'm just implementing these two formulas. So it knows I have second component of x here, first component of x here, and that's what I have here. So that defines my g. And for an initial guess, I'm dealing with the domain x1, x2, both between 0 and 1. So for initial guess, I'll just choose x1, x2, both equal to 1/2. So it's the center of that square. Okay. So, what I'm going to do is I'm going to plot. First, I'm going to make sure I have no figure windows open. So close all. So now I'm going to run a command x equals g of x to carry out an iteration. And then I'm going to plot x2 against x1 as a circle. And I'm then going to do hold on so I can see all the circles as I continue the iteration. And I'm also going to put this command in figure 1 to bring it to the forefront. This will carry out the iteration and then plot it and show it. Let's see what it looks like. Okay, so I started at 1/2, 1/2. That's right around here. So the iteration moved down here. But now I'm going to keep doing this. Okay. So first iterate was down here. And I don't know if you can see this very well. The second iterate is a red circle that's up here. And what I'm hoping is as I perform more iterations, we'll be able to see it better. Find out. Okay, first iterate, second iterate, third iterate is over here. Doesn't look very convergent. Okay, so first, second, third, fourth, it's kind of bouncing around. Okay, I'm gonna change the format of this figure window. Use presentation style. Okay, now the iterates are easier to see. Okay. So far this is not a good sign. Considering it started at my initial guess is 1/2, 1/2. And so at first, second, third, fourth, and I'm just going to keep going and see where we're at. Oh, unfortunately, it's not. I was hoping to continue plotting them in a bigger marker size. So, okay. I'll just apply this. Sorry about this. Okay, so yeah, it's definitely not converging anything. Now we can see the whole domain, well, almost the whole domain, 0 to 1 in y, 0.1 to 1 in x. The iterates are what you would find if I keep going. Many iterations, and I'll make them bold. Is the iterates seem to be gravitating towards the corners. Now we can see the whole domain, 0 to 1 in x, 0 to 1 in y. So it just keeps, iterates keep getting closer and closer to the corners of a square. So this is not working.
It's like a spiral of some sort.
Yeah, so it looks kind of cool. It's just not converging. Okay, so we'll like to get an idea as to why this is happening. Here's the Jacobian for this g. So taking the partial derivatives of these two component functions with respect to x1 and x2. And then we have 0 on the diagonal, and then we have these off-diagonal entries here. And what happens is, so for the corners, x1 and x2 both are converging to either 0 or 1. So for example, as x1 is approaching 1, this entry is approaching 2. So there's going to be a norm, like a 1 norm or infinity norm, that's going to be greater than 1. Okay, so the conditions for convergence are not necessarily being satisfied. But we've seen in other examples, if you apply fixed-point iteration, you see that it's diverging. You can try rewriting G, come up with something different. So the alternative is rewrite the equations. X1 is square root of x2. X2 is defined to be this way for a given circle. Okay. And okay, let's try a different sheet. Okay, so I'll define G. X is the root x2, the root 1 minus x1 squared. Okay. Yeah, it's getting incredibly hot in here. Get some water. Okay. So now I'll set the river figure. Then I'll set x equal to 1/2. I'll see what happens to either this time. It's going to do a bunch of these. Not to see a pattern. Okay. Did I do it right one? Make sure I, yeah. Still not converging. Square root of 2, square root of 1 minus x1 squared. Oh, wait. Okay. Yeah, it is converging. It's going round and round, but at least it's converging on a particular point. And if I keep going, yeah, okay. So it's converging in a rather unusual way. I'll
Looks pretty.
yeah, it certainly does. Okay. So now what I'll do is the Jacobian matrix in this case is given here. So what I'm going to do is I'm going to define this matrix. So Jacobian matrix near fixed point. So J is equal to a 0 and then 1 over 2 at 0, 1 over 2 times square root of x2. Then I have this expression, x1 over square root of 1 minus x2. Yeah, squared. Okay. Oh, there's a typo here. This should be x1. Yeah. This function only depends on x2. This one only depends on x1. So it's fixed out in the code. And 0. So here's the Jacobian matrix evaluated at the point where that appears to be convergent to. So now I'm going to compute the eigenvalues. I of j. Okay. Yeah, and so the spectral radius is the maximum absolute value of these. So it's less than 1. That is a condition that we need to have satisfied for convergence. Now it's close to 1, which is why it's converging rather slowly, but it's still converging. if it's possible to find an inverse for G, the same principle as in a single variable case still applies, where you have x equals G of x is equivalent to x equals G inverse of x. So that can give you a way to rearrange a fixed point iteration if it's working. Of course, in multivariable, that's a lot harder to do in a single variable. All right, so questions about fixed point iteration for a system? Yeah.
So that part where we have this mapping, a square mapping, like it maps to itself.
Yeah.
That's a theorem, but Brouwer.
Brouwer's fixed point theorem.
Yeah.
Now, this is something we dealt with in the case of a single variable. I'm assuming it's also multivariable, although the intermediate value theorem itself doesn't generalize to higher dimensions. That's tricky. Okay. So crazy hot in here, but better than was. Okay, Newton's method. Now, Newton's method for a single equation, the way it's written before was x equals 1 equals xk minus f of xk divided by f prime of xk. But here I've written it a little differently. Instead of dividing by f prime of xk, I'm multiplying by its multiplicative inverse. The reason why I'm writing it this way is that it's easier to see how you generalize the system, because for the system equations f x equals 0, you no longer have a derivative. You have a Jacobian matrix. You can't divide by a matrix. What you do is you multiply by the inverse. So the main step of Newton's method for a system is a natural generalization of what we see for a single equation. So new iterate equals previous iterate minus the inverse of the Jacobian matrix evaluated at the previous iterate times the function value at that iterate. Another way to think of it is new iterate equals previous iterate plus this factor here, sk, with an s for step. So what you're doing is you're really solving this system of equations. Jacobian times step is equal to minus f. And then that is how you proceed from one iterate to the next. Yeah.
So Newton's method for a simple equation, in the formula. So that's a multiplicative inverse.
Yeah.
Right? Now, so I like how it automatically translates to an inverse of a matrix. How do we know that those two operations, there's still different types of inverses. That one is multiplicative and that one is a matrix.
Yeah, but what's the inverse of a 1 by 1 matrix? Yeah, so it literally is the inverse. Okay. So generally you would not compute the inverse of a Jacobian matrix because that'd be quite expensive. You just solve this system at every iteration, because the Jacobian depends on xk. So unless you have a particularly simple function f, you have to recompute this matrix each time. Now, I won't go through the details here, but does the Newton's method converges quadratically in a single variable case? It also converges quadratically in the case of a system. But if the Jacobian is singular at the root, then we have a problem, because then the system can't be solved. Just like if the in a single variable case, if the derivative at the root is 0, then Newton's method only converges linearly. So both cases, the scalar or single equation or system, if the Jacobian has a equals 0 in a single equation case, or its determinant is 0, then Newton's method has problems. Now, Newton's method over a system has some problems. Because for a single equation, one of the knocks against Newton's method is that each iteration is fixed. You can evaluate f you get to evaluate f prime too. Well, this gets even worse when it's a system of equations, because now if you have n equations and n unknowns, you have to evaluate n squared partial derivatives. That's bad enough. Then you got to solve this system. That takes order n cubed operations. So each iteration of Newton's method for a system is horrendously expensive, especially if the matrix is large. So we'd like to do something different. And this leads to a method known as Royden's method. And actually, you can think of it as an attempt to generalize the secant method. The secant method doesn't really generalize in a straightforward way to systems, but there are quasi-Newton methods, which Royden's method is an example of, that use ideas from the secant method to improve efficiency. So the idea behind Royden's method is this. Instead of solving this system at every iteration where we recompute the Jacobian of f at xk, we use an approximate Jacobian. So how do I define approximate Jacobian? So for the first iteration, the first approximate Jacobian, which I'll call A0, is the true Jacobian. So in this case, we bite the bullet and incur the expense. But then, when we go from one iteration to the next, we use an approximation. And here's the idea. I want the Jacobian times the difference in my most recent x values to be equal to the difference in my most recent f values. Now, keep in mind, everything here is either a matrix or a vector. So we can't divide. But suppose we could. This is very non-rigorous here. If I were to divide by the difference in x's, I'd have AK equals change in f divided by change in x. It's a secant line approximation of the. So in other words, this approximate derivative is based on, you think that in a single variable, it'd be a difference quotient. Just like in the secant method, you replace f prime with exactly what you would get if you could divide, a difference quotient involving xk and q minus 1. Now, since we can't divide, we phrase the condition this way. Approximate derivative times difference in x equals difference in f. So AK has set by this condition. But really what we're saying is AK times a known vector equals another known vector. So that would mean that AK approximately equals what the Jacobian would give, at least in this direction. Meanwhile, among all directions orthogonal to this, our new approximate Jacobian is equal to our previous approximate Jacobian. So we really only care what happens along this direction. That's getting us closer to the root. Now, the way that we do this was by what's called a rank 1 update. So if you have your previous Jacobian, it's AK minus 1, you modify AK minus 1 to get AK by adding on this term. Now, this fraction right here is a vector. So we have a vector in the numerator, and we have a number in the denominator. So this whole fraction is a vector, column vector. Here we're multiplying by a vector transpose. So it's a row vector. So we have column vector times row vector. So here's another way to look at it. This whole fraction I'm describing as UK. When you have a column vector multiplied on the right by a row vector, that's called an outer product. That is a matrix. I think I brought it up in here before. An outer product of vectors has rank 1. So that's why this is called a rank 1 update. Now, so the nice thing is, when you have a matrix that's defined as a rank 1 update of another matrix, it's actually easy to get the inverse. Because we have this formula, it's called a Sherman-Morrison formula. So if this inverse is known, then to get the new inverse, you just have to add on this term. So Sherman-Morrison formula gives the formula for the inverse of a rank 1 update of a matrix whose inverse is known. So what that means is, instead of computing, A1, A2, A3, etc., we can just compute these inverses. Now, I know I say never, never, ever explicitly compute the inverse, but in this limited situation where it's a rank 1 update, it's actually a lot more practical to do so. Because this update takes only order n squared operations rather than n cubed. So what you can do is you can solve your approximation of this system by multiplying the appropriate vector by an inverse. So now we're just solving systems using only matrix vector multiplication that takes order n squared operations instead of a general n cubed. So now each iteration is a whole lot more efficient than if we were to actually use Newton's method. Here I'm contrasting the outer product, so U V transpose is an outer product, whereas U transpose V, so notice a different placement of the transpose. It's an inner product, which is a number. Then when you take an outer product, U V transpose times a vector X, because matrix multiplication is associative, V transpose X, that's the number, and the result is guaranteed to be a multiple of U. So outer products are used often in numerical algebra. Quite unique. I want to show you something in the text about this method. Further reading, if you will. So in the text, I won't go through it here, but in the text, I have more detailed, more information about the derivation of this rank 1 update, because we want this matrix AK to satisfy these conditions. That so here, if we want, so if I have B being a rank 1 update of A, so this is a more abstract version of what I was just showing you, the avoidance method. Then if I know that A times X is equal to a specific vector U, that's part of the outer product, then I have a way of figuring out the inverse of B. So here, this is on page 442, is where I derive the Sherman-Morrison formula. So how to solve this generic problem? If I'm given a matrix C, which is like my previous Jacobian, I want to construct a matrix D, which is my new approximate Jacobian. And if I have conditions to satisfy that my unknown matrix D satisfies this condition, D times a specific vector W equals a specific vector C. But then for all vectors Y that are orthogonal to a given vector G, D equals C. Then this is how you construct D. It's equal to C plus this outer product here. So this formula is used to derive the Sherman-Morrison formula right here, like in the general case. And then that Sherman-Morrison formula is applied to figure out the each approximate inverse for avoidance method. And this is the algorithm for avoidance method right here. That here we compute the true Jacobian in the first iteration. We go ahead and solve this system to get our step from our initial guess to our next iterate, our second iterate, x1. And then, so here I do need to compute this inverse, A0 inverse. But then from this point on, as the iteration proceeds, each new inverse is equal to a previous inverse plus this term that involves an outer product. So this update of the inverse takes only order n squared operations. And then when I compute this right here, my step for the next Newton iteration, I'm taking an approximate inverse and multiplying it by f of xk. Here, even though it looks like I'm solving a system, it looks like I'm solving a system, but really what I'm doing is forming a matrix vector multiplication, again, order n squared. So each iteration of Boyden's method takes order n squared operations instead of n cubes, which is what Newton's would do. Now, in this class, we get into differential equations, and once we get to systems that come with differential equations, like boundary value problems, we'll have occasion to solve a system of nonlinear equations, and I'll bring up Newton's method in particular. So that's why I wanted to cover this section, to give you an idea as to how systems of nonlinear equations can be solved by generalizing null about for a single equation. Okay, but I just want to make you aware, in case you're interested, of more of the derivation of these approximate Jacobians and where the Sherman-Morrison formula comes from. It's a bit of an algebraic mess, which is why I didn't do it here. Okay. Now that I pulled the room down, I was also afraid of a pass out or something in the heat. Yeah, it was kind of scary. So, okay. But I also come to the end of the notes. So, questions about anything? I probably hear my door slam all afternoon from these windows open, but not my door, but this door. The classroom slam all afternoon, but okay. Well, I'll try. This is the last class before spring break.
Yeah.
So I won't see you all for a while. So for Monday after spring break, which will be the 18th of March, 12 days from now, so starting from then until the rest of the semester, it's all differential equations all the time.